I'll send y'all an email out sometime soon in the next day or so. And I did post the exams, so the old exam, the most recent exam is up there. But if you didn't get it, yeah, I think I might just have one of yours. Mark's not here, right? But Chris, I have yours. So we've been dealing with convex and concave mirrors, just sort of to remind you. Concave, this is like the one that we set the paper on fire. We did that, right, last time? Yeah, the one that looks like this. You stand in front of it, right here. Right, it produces a few different types of images that we'll see. This is also called a converging mirror, because light rays that come in will converge. Right there, set you on fire or whatever. The focal length for this is positive. It's greater than 0. And also remember, just in general for mirrors, that the focal length is 1/2 the center of curvature. The center of curvature is the radius of that sphere from which your mirror has been formed. Also for mirrors, and we'll see this for lenses as well, the magnification is -Q/P. The mirror equation holds, that is 1/F equals 1/Q plus 1/P. We have another type of mirror. It looks like this. This is a convex mirror. It's also sometimes called a diverging mirror, because light rays that come into the mirror like this will diverge. Right? And of course your object would be over here, and it would always produce an image that is smaller than and upright and virtual. We'll see that in a bit. We're going to do some ray tracing diagrams, which you'll also see on your exam. A couple things about just the signs. A negative magnification means that it is inverted. A positive magnification means it's upright. A negative image distance means it's virtual. And a positive image distance plus Q means it's a real image. All right, a real image is just an image that you can project onto a screen. These will all come into play. We'll do the ray tracing diagrams, and we'll see how all these different images are formed. Let's try this clicker question now. All this is in your notes, should be, but it's been a while. So let's try this. We have a convex mirror mounted high on a wall to help people avoid collisions. It's like in a hospital, right? They have those big mirrors, convex, like a security mirror. Has a radius of curvature of 2 meters. What is the magnification of a patient 5 meters from the mirror? Bring up our clicker. What is the magnification of this person? don't forget here that the focal length of a convex mirror, the focal length is always negative. It's always less than 0. So if you find your focal length, it doesn't say explicitly that it's negative, but it is because it's a convex mirror. And you can remember that because you have this mirror, you're on this side of it, and the focal point is back behind the mirror, sort of in that virtual space that we talk about. And also, what type of images, if you look in one of these convex mirrors, what type of image what does it look like? Are you bigger or smaller usually? You're always smaller in a convex mirror. And are you ever upside down in a convex mirror? Never upside down. So the magnification will reflect that it's smaller and upright. So you can eliminate some answers. All right, still on about 5 more seconds. I'll say we're at 325. Stop at 325. All right, let's see. So we have a lot of B and C. It cannot be B, and why is that? Why can it not be B? Right, that would be a negative magnification, which would mean that it would be upside down. And in a convex mirror, it's never upside down. We'll see that with the ray tracing diagrams, but you probably just know this from experience, that in those security mirrors, you're always upright. You're always smaller, and you're always upright. So we can get rid of a couple of options here just from that. We can get rid of B, and then we can also get rid of D, right? Because D would say that the image is bigger than the object. So I'm guessing it's C here from your responses. I'm going to go and mark C, and then we'll see. All right, so our radius of curvature is 2 meters. That means that our focal length is 1/2 of that, and because it's a convex mirror, it's going to be -1 meter. We have the patient is 5 meters from the mirror. That's going to be our P or our Q? No, P is our object distance. So P is equal to 5 meters. All right, so just remember these terms. P is object, Q is image. I know it's been a whole week. All right, so P is our object distance and Q is our image distance. All right, and that's all we need. So now we can find from our mirror equation, 1 over Q plus 1 over P, we can find Q. At -1, what is this? You want to tell me? This value is? What is it? Let's see this. Yeah. Is it 6 over? It's 6 over 5. 5 over 6, yeah. All right. So -5 over 6 is our image distance. So just a little under a meter, and then we can find our magnification, which is -Q over P. So that's -5 over 6 over 5. Which is, -5 over 6 over 5, which is going to be +1 over 6 meters. Is that 0.16? Yeah. It is, okay. All right. In this, it's really keeping track of all those signs and making sure that those are correct, and then also just knowing what type of mirrors produce what type of images, and that'll really help you in these problems. You'll probably see a couple of these on the test, a couple of free response in this order. Yeah, Mary?
Wouldn't that be -1 minus 1 over 5?
Right here?
Right.
Right, so that's going to be -1 minus 1 over 5, which is 6 over 5, -6 over 5, and then you have to invert it, so it's -5 over 6. It's hard to come back, isn't it? It's hard to come back to school for y'all? It was hard for me too. So, all right, let's do some ray diagrams. Because if you really master these ray diagrams, which you could also see on the test, I haven't decided yet, but I'll try to give y'all a heads up as to whether or not you'll actually have to draw ray diagrams. It'll help you in these types of problems because you'll know what type of images are formed by what types of mirrors. First of all, there are just a few rules for drawing rays for spherical mirrors, and these will look very similar for spherical lenses as well, which we're going to get to next. The first one is you draw a ray parallel to the axis. And then it reflects back through the focal point. And this is how we define the focal point. The second, you'll draw a ray through the focal point, and it reflects back parallel to the axis. And then the next is draw a ray through the center of curvature. And it reflects back on itself. Okay, so I'll sort of give you a little sketch of this, though we're going to sketch it out. This is my focal point, this is my center of curvature. If I have a ray that comes like that, it's going to reflect back on itself and not bend at all, or not bounce at all. And then you can also draw a ray to the center of the mirror. And the reflected ray follows the law of reflection. That is that theta I is equal to theta R. All of these rays follow the law of reflection, but this one in particular is pretty easy to see. Let me show you. So if this is a ray that comes in, it comes to the center of the mirror, and it bounces off so that these two angles are equal. And we'll use that to sort of to verify where our images are. A couple of things about these: that will always position the object on the optical axis and let rays originate from the top of the object. So that means, let's say that this is my optical axis right here, this line. My mirror, for example, would be right there, and I would have an object that would be drawn with its base at the optical axis. That's the axis that bisects the mirror. And your rays are always going to originate from here. So I would have a ray that would come along parallel to the axis like that, and then it would go through the focal point. And then I could have another ray that will go through the focal point like this and parallel to the axis. And where those two rays cross is where the object is going to be. So my two rays will cross like that, and it will show where the top of the object is. So the image, in this case, we would know is inverted. Where the two rays cross show where the top of the image is. It's not, however, like this, and this is sort of a common mistake that students make. You would not draw your image like this, right? Because the base of your image is always going to be at the base of the optical axis. We'll see that as we go through. Right, so your image is located where these reflected rays cross. Right, I'm going to draw all the rays. These are in your homework as well, so if you just sort of lose track along the way, you'll find there are videos online that show you how to draw all the rays. And likely I'll just give you one problem on the exam and say just draw the ray diagrams for this mirror or for this lens. And for the lenses, the rules are going to be very similar. All right, so for concave mirrors, we'll have 3 different scenarios. And then for convex mirrors, we'll just have one scenario. For concave mirrors, your objects can be in 3 different locations. It can be outside the focal point. It can be at the focal point. Or it can be inside the focal point. Outside the focal point, your object would be here. at the focal point, your object will be located there, and then inside the focal point, your object will be located there. So you can move your object with relation to the focal point. Remember, we had that concave mirror. If you held it up really close to your face, how did you look? No, if you held it up close to your face, it was like a makeup mirror, right? So you look really big and upright, but if you held it further back, you saw what? How'd y'all look? You were upside down. And then somewhere in between, actually, your image just went away. So let me just sort of summarize this. We'll see these images in just a bit, but if you're outside the focal point, you will have an inverted, and it turns out to be a real image. Okay. If you're at the focal point, there's no image at all. Sort of in between those two images, the image just goes fuzzy in the mirror, and that's when you're at the focal point. There's no image at all. And if you're inside the focal point, you have an upright virtual image. And that image is bigger, a magnification greater than 1. It's bigger. That's like the makeup mirror. So if you remember that mirror, sort of those 3 different scenarios, outside the focal point, you're upside down. It's a real image. If you're at the focal point, there's no image at all. And if you're inside the focal point, it's an upright virtual image. Let me go through. I'm going to show you how to draw these rays. If you're an engineer, you might eventually come upon some ray tracing programs, and there are actually quite a lot. I think ZMAX is the most common industrial ray tracing program, where if you design a system of optics, you can trace the rays through the optics and figure out what kind of image you'll get on the outside. And it basically does this. It just follows the law of reflection or the law of refraction, as it may be if you're dealing with lenses, and draws these rays. But it'll draw like millions of rays to actually determine what is the image, the exact image that you get. All right, so I'm going to draw a couple of rays on each one, but remember there are 4 rays that we can draw, and then I'll try to put it together in just a second. But right now I'm just going to draw them 2 different rays on each diagram. And on the test, it'll be useful to have a ruler. If you don't have a ruler, you can just take a sheet of paper and fold it over, and it makes for a nice straight edge. So for the first rule, remember that was parallel to the axis. Parallel to the axis, and then where did it go? Right, remember this is how we define the focal point. Parallel to the axis and through the focal point. So this is number 1. Number 2 was through the focal point and parallel to the axis. Right, this is number 2. Actually, I'm just going to draw them all on this one mirror here so you can see where they come together. But I have different colors, so you might not be able to see yours quite as well. Number 3, I think, was green. Is that right? Yeah, so number 3 is green, and that was through the center of curvature and then back on itself. So remember, my rays are originating at the top of the object. I have it go through the center of curvature. It'll go in that direction, and then it'll reflect back on itself. All right, so already I see now where my image is. It's where these 3 rays all come together. I can draw my happy face here. But remember, it's going to be upside down, so it'll look like that. And then I can draw one more ray. This is ray number 4. I just draw it to the center of the mirror, and then it reflects following the law of reflection. This is really just to verify where your image is. We already know where it is. It's going to look like this. And those 2 angles will be the same. Like that. So that's number 4. Okay. And number 3 was this one. That one's probably the easiest ray diagram to draw of, well, except for the second one. This is probably the easiest. These are all real rays because the rays cross on the real side of the mirror, on the same side as the object. This produces what type of image? This is a real image. It's an inverted image. And in this case, it happens to be smaller. So we have here a real inverted image. I know that it's real because it's on the real side of the mirror. So I could plot down the screen right here, and I would see this image on the screen. Kind of like what y'all did in the lab when you used the lenses. You could put a screen there and see the image on the screen, see it projected onto the screen. So that is a real inverted image. Now, the second one is inside the focal point. Oh, this should say at the focal point, I'm sorry. So this one is at the focal point. We can really only draw a couple of rays here. I can draw a ray parallel to the axis and through the focal point. Parallel to the axis. Through the focal point. Remember, this was our number 1 rule. It's the definition of the focal point. Then we can't draw number 2 because we can't draw a ray through the focal point, but I can draw number 3 just through the center of curvature. Now I'm going to draw a ray up like this. I draw it such that it's like it's originating from the center of curvature. All right, so I draw this ray that looks like it's coming from the center of curvature, and then it's going to reflect back on itself. So it's going to go up and then reflect back down in this direction. So this is rule number 3. I can draw rule number 4 as well. That is that it will just go to the center of the mirror and follow the law of reflection. What can you tell me about these rays? What do they look like? Geometrically, how would you describe them? They're parallel. The parallel rays never do what? They never converge. They never cross. Right? So this one is going to produce no image. And we can see that from the ray diagram. Will produce no image at all. If you're looking in a mirror, it would just look really fuzzy because the rays wouldn't be crossing all at the same point. They would be sort of crossing at slightly different points, and it would just make the image look fuzzy. We've seen this already. You can show that if P equals F, then Q approaches infinity. We did that before. If we do our mirror equation, 1 over F equals 1 over F plus 1 over Q. That means 1 over Q equals 0. Our Q approaches infinity. Right. If Q goes really big, 1 over Q goes to 0. All right, and then the third one, for the concave mirror, and this is probably the most difficult of these 3, is inside the focal point. I'm going to draw them on 2 separate ones because they get kind of complicated. You can draw the first one through the focal point and then parallel to the axis. I'm going to draw a ray that goes up to the mirror such that if I were to trace it back, it looks like it's originating from the focal point. And then it goes parallel to the axis. This is ray number 1. And then ray number 2. Oh my gosh, what is ray number 2? Oh, parallel to the axis. I'm sorry, that was ray number 2, wasn't it? Through the focal point and parallel to the axis? Is that right? Yeah, I'm sorry, I got this mixed up. So this is actually number 2. No. You could see this in a couple of different ways. I could just give you a mirror with an object drawn on it, and I just ask you to draw the rays. And likely you'll have to do that. And also, you could also see multiple choice, where I give you a number of rays and ask you which one is correct or incorrect. If you look back at the old exam, you'll see some examples. Okay. So likely you're just going to have to draw rays for either a mirror or a lens. So this was number 2. Number 1 is parallel to the axis and through the focal point. So parallel to the axis and then through the focal point. Like that. Right. So this is number 1. Now these rays are not parallel, nor are they convergent. These are divergent rays. That means that they're never going to cross on the real side of the mirror. But if I trace them back, we'll find that they do trace on the back side of the mirror. Like this. Right? We saw these before with flat mirrors. These are called virtual rays. It's like they're an extension of the real rays back into that virtual space. And then I can see my image is going to be right here. Right, so this is an upright, virtual, always magnified image. So the magnification here is always greater than 1, greater than positive 1 in fact, because it's also upright. I can draw the other rays. You can either do it on the same diagram or I'm going to draw it down here. Number 3 goes through the center of curvature and then back on itself. So I draw a ray up into the mirror as if it's originating from the center of curvature in that way, but then it reflects back on itself. It comes up that direction, and then it reflects back on itself. And then I'm going to go ahead and trace back the virtual ray. So right there. And then finally I can draw that 4th ray, which is just down to the center of the mirror, following the law of reflection. And then I can trace it back like that. And so my image is right there. You could also draw them on this other diagram. I'll try to sketch it in just so you can see, but it's difficult to see. Yeah, they're not crossing right, but you get the idea. Follow me on this. See how you can draw these rays. Where these rays are crossing, they would also cross in here. You sort of have to be careful in how you're drawing them so that your lines are all straight for them to show up correctly. All right. This one's a little more difficult to do because you have to trace those virtual rays back. You with me so far? All right. The last one is similarly difficult because you're dealing a lot with virtual rays, and that's the convex mirror. For convex mirrors, the focal point is behind the mirror, so the focal length is negative. So if I look at the mirror equation, 1 over F equals 1 over Q plus 1 over P. If the focal length is negative, I'm just going to make this a negative value. Then I get a Q that's also negative, because I would have 1 over negative F minus 1 over P equals 1 over Q. So regardless of what the magnitude of F or P are, Q is always negative. That means that a convex mirror is going to produce what type of image? If I have a negative image distance, what type of image is that? That's a virtual image. So negative Q means that it's a virtual image. So if Q is always negative, a convex mirror always produces a virtual image. So we're going to draw arrays very similarly. We'll follow the same 4 rules, but they'll just work out a little bit differently. The first rule is you draw it parallel to the axis. And remember, this is a diverging mirror, so anytime rays come in parallel, they're going to diverge from one another, but they're going to diverge in such a way that if you were to trace it back, it would go through the focal point. So it's going to diverge up in this direction, such that if I traced it back, it would go through the focal point. Right, so this is ray number 1. And then I can draw ray number 2, which is through the focal point, and then parallel to the axis. But you can't have a ray that goes through the focal point here because it's in that virtual space. So I'm going to have a ray that comes up to the mirror, such that if I traced it forward, it would go through the focal point. And then it goes parallel to the axis. So this is rule number 2. these are divergent rays, right? So they're never going to cross. So to find where my image is, I'm going to trace them back and find out where the virtual rays cross. Is this a virtual ray right here? No, this is not a virtual ray. Our virtual ray is the reflected ray that's traced back. So I need to trace this ray back to find out where my image is. So I'm going to erase this little dotted lines here, because I just used that to help me find where that red ray was drawn. So my virtual ray then for this red line, for rule number 2, is going to be right there. We can draw the others as well. Rule number 3, through the center of curvature. I'll just draw it here. You can draw it on the other diagram if you like. You're going to have a ray that originates at the top. It's going to go forward such that if you were to trace it out, it would go through the center of curvature. And now this isn't technically the virtual ray, but because this ray will actually reflect back on itself, it's the same as the virtual ray. So I have this ray that goes up like that, reflects back on itself, and then I can trace that reflected ray back, and I'll find that it follows that path back through the center of curvature. That's our third ray. And then our fourth ray is just sort of to verify, we already know our image is, but it's going to go to the center of the mirror, like that, and then reflect back on itself. Or reflect following using the law of reflection. And then I can trace it back right there. So my image is going to be right here. Notice that it's upright, it's smaller, and it's virtual image. This is ray number 4, and this is ray number 3. On the test, I would just have you draw 3 rays, but you really only need 2 rays to determine your images. So I would have you draw 3 rays.
You can use any.
You can use any 2, is that what you said?
Mm-hmm.
Yeah, you can use any 2 rays.
And don't give it a
Right. But on the test, I'll require 3 rays. You don't need to know all 4. Right. Some of them are more difficult than others. That fourth one that we draw is usually just sort of thrown in to help you determine where the image is, just to make sure that you're doing it right. But they should all cross at the same point, either the virtual or the real rays, where the image is. Okay? I know that's a little dry for Monday morning, but it's fairly useful. It'll help you in some of the problems if you just know what types of images are formed by what types of mirrors. Let's try a couple little problems. Let's see, I think I had a mistake in this. Yeah, on this question, instead of having the image here, let's say that the image is over here. All right, I want you to tell me what type of mirror has produced this image. So this is a real or virtual image?
virtual.
So the virtual image is obviously upright and it's magnified. Virtual, upright, magnified image. All right, so a few more seconds. I'll stop at 50. Let's try a couple others. So let's say instead that the image isn't here, it is no, let's say the image is right here. This is our image. What kind of mirror has produced this image? This is a real inverted image.
Cool.
types of mirrors. We have flat, convex, and concave. Flat mirrors produce a virtual image that's the same size. Convex mirrors produce a virtual image that's smaller. And then concave can produce different types of images depending on where the object is. 3 different scenarios. No image at all, real, inverted image, or virtual, upright, bigger image. Just a few more seconds. I'll stop at 58. Okay, very good. So it's the same type of mirror as before. It's just the object is in a different place with regards to the focal point. And then let's try one other. This image is, what, real or virtual? Virtual. How big is it compared to the object? The same size as the object. It's also equidistant from the mirror as the object. Equidistant? Have y'all been using that word?
Doesn't come up in much normal conversation.
Orthogonal? You know, use orthogonal?
Oh, yeah.
Right. Yeah, who's it?
I'm just getting confused. Which one is the real image?
Okay, for mirrors, the real image is on the same side as the object.
Okay.
Right. The way I remember this is like, if I have a mirror, I can't put something behind the mirror. I put it in my mirror, that doesn't really affect the mirror at all. But it's on the same side as the object. That's like the real side of the mirror.
Okay.
The back side is like that virtual poltergeist world. The front side is the real side.
So for our convex, that image that we draw is not really the real image?
That's not a real image.
That's a virtual image.
Right, a convex mirror is not real. Okay. Now with lenses, it's going to be a little bit different. It's going to be sort of the opposite of that. All right, just a few more seconds.
It's a lie. Oh.
Okay, very good. This is a flat mirror. And the reason I know this is because it's the same size as the object, first of all, and then also it's equidistant. The Q is equal to negative P. All right, let's go to this next one. Which of these mirrors will produce a virtual image under particular conditions? Concave, convex, or flat, or some combination of those?
That's the second question versus the first question.
What's that?
That's the second question versus the first question.
Second question. I don't follow.
This question.
Oh.
The first one.
Sort of, yeah, it's similar. But which of these mirrors, concave, convex, or flat, will produce a virtual image? Under a set of conditions, it's possible to produce a virtual image. Alright, so a few more seconds. I'll stop at 1:30. Okay, A is right. Don't forget the flat mirror also produces a virtual image. So concave mirror will produce a virtual image if the object is in front of the focal point. Convex mirrors always produce virtual images, and flat mirrors likewise always produce virtual images. So it's really the concave that switches up depending on where you are with regards to the focal point. All right, let's look at a couple of different phenomena that occur because of refraction by the atmosphere. There are two things that we'll look at. First is just sort of when sunset occurs, and then the second thing will be mirages. That might take us up to the end, we'll see. So there are two phenomena. The first is that the sun appears at dusk, or at sunset. even though it is below the horizon. So we don't know this is actually happening, but it does occur. It just sort of looks like the sun is there. But in fact, the sun's not there, that the light rays are bending so that you can see it. So it sort of happens like this. If you're sitting on the Earth, here I am, looks like I'm sort of in Alaska or whatever. The sun's rays, if they just went straight, they would not reach me because the sun has already dropped below the horizon. But because of the atmosphere's refraction, the refraction of the light, that light rays actually come, and then they bend through the atmosphere, and they come to my eye where I can see it. So it just looks like I see the sun like normal, except that it's not really there, that it's already dropped below the horizon. I'm just seeing the light rays as they're being bent. Was it?
So would that happen the same thing to the other side too?
Sure. Yeah. But I mean, I'm drawing them a lot closer than they really are. So you would.
Yeah, I was
right.
about to say that that's like
Uh-huh.
25%.
Right.
That
Uh-huh.
is in the dark only.
Right. So, yeah, this is obviously exaggerated, but you can, when you can just see the sun, especially if you're out on the water and you can see the sun just say half below the horizon, the sun is actually below the horizon already. It's just that some of those rays are being bent by the atmosphere, and so you're able to see them.
Did you ever hear of the cherry picker thing?
The cherry, what, that you can see the sun in a
That
cherry picker?
I think it is, if you have the cherry picker at the lowest point and you sit next to the ocean, because that's just where the curve, just all like next to the Gulf or something.
Uh-huh.
And then whenever it just goes below, you lift the cherry picker up like 10, 20 feet,
You
you'll
can
be able to
still
see the sunset set again.
Mm-hmm, yeah. Right, because you lift yourself, you can see the horizon from a further distance if you're up higher, right? Because where the Earth is a ball, right? It's a sphere, it's not flat.
Supposedly you can only see like 31 miles because that's the part the sun can see before it just dips below the
Right.
horizon.
Mm-hmm. Yeah.
Just can't get into an elevator. Just go high.
Right. Just are in a
Actually,
plane,
it's
right?
kind of cool, and that really cool, how do you, what is that name of that really tall building in Dubai?
Oh, I don't know. I know what you're talking about there.
Can't.
But the same occurs in an airplane, right? If you're flying into an airport at sunset, roughly, it'll look really bright while you're up in the airplane, but then you drop down and it's completely dark, right? So, all right. The other is mirages. You see mirages on a hot day. We actually see these a lot here, yes, because we have a lot of hot days. But you normally think of these as being in the desert because it's really hot there. And so what happens here is that you look out in the distance and it looks like you see what? On the ground. It looks like you see water on the
It's actually
ground.
the sky.
Because you're seeing a reflection of something. So for example, say you saw a camel out in the desert, you would see a slight reflection of the camel below it. And it looks then like the camel is standing in water. Because in our mind we think, well, water reflects light and it's producing a reflection of the camel. But what's actually happening is that you have light rays that are coming to you just from the camel, but then light rays also bend down. And because you have this blanket of hot air above the desert, it's going to bend upwards and come to your eye. And then in your mind you think, well, this light ray is coming from here, and so you see a camel, actually a reflection of a camel, or whatever it is, happens to be. I'll show you a picture in just a second, it's kind of cool. So light rays near the hot ground are refracted and appear to originate from an actual object or from an object below the actual object. And this looks like a reflection to you. Even though it's not really reflection, it's really a phenomenon of refraction. So then you assume that the object, a camel like this, is standing in water. And we just assume that because water reflects. It looks like it's standing in a lake or whatever. However, these mirages are not a result of reflection. Even though it looks like reflection, it's not really a reflection. They're purely a refractive phenomenon.
Supposedly they thought it was like almost the exact opposite of this kind of for the Titanic. The cold air was curving the air in such a way that they didn't see the.
Seriously?
Yeah.
Let me me show you a little clip. This is a guy, he sort of looks like Dr. Schultz. You know Dr. Schultz? Yeah, he sort of looks like him. But talking about mirages and how they occur. And he shows some really cool pictures of mirages out in the desert. But if you're ever driving out on the road, I mean, even yesterday we saw a bunch of mirages, even though it wasn't that hot. Because the road gets really hot as the sun is beating onto it, and it can be a lot hotter than the surrounding area, and you see a lot of mirages. See, I think we'll wrap up after this, so you can, if you want to put your stuff away, that's fine.
Video.
Oh shoot, yeah.